a routing container dies every 30 minutes during peak hours. The team assumed a memory leak, but the real culprit was the graph database client's default connection pool, 100 connections, each caching 50 MB of root data, consuming the entire 4 GB heap. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design Google Maps. Google Maps is a distributed system that ingests map data, geocodes addresses, computes routes, and serves real-time traffic overlays. It combines graph databases, spatial indexing, and stream processing to deliver a seamless experience. Before tiles, maps were monolithic images. Google popularized the tile grid. Each tile is a 256x256 PNG at a specific zoom level. Tiles are immutable and cacheable, allowing aggressive content delivery network caching. The tile pyramid precomputes popular zoom levels and serves them from blob storage. Here's a simplified tile server. It uses an LRU cache with 10K entries per node. On a miss, it checks blob storage, and if that fails, it renders the tile on the fly. Cache hit ratio is over 99% for popular tiles. Geocoding converts an address to coordinates. The system tokenizes the address into a hierarchy and traverses a trie for prefix matching. To handle ambiguous addresses like Main Street, it uses the user's IP geohash to bias results. This simplified geocoder tokenizes the address and traverses the trie. It returns up to 5 results sorted by population. The real system also uses a geohash prefix from the user's IP to filter results, reducing ambiguity by 90%. Dijkstra on a graph with 500 million nodes is too slow. Google uses contraction hierarchies, which precompute shortcuts between important nodes. During a query, bidirectional Dijkstra runs on the contracted graph, giving sub-millisecond results. Real-time traffic is applied as a post-processing penalty. Here's a simplified CH-based router. It runs bidirectional Dijkstra on the contracted graph, then applies traffic penalties to each edge. This is why traffic-aware routes are slightly slower to compute. Traffic data comes from GPS pings, road sensors, and incident reports. The pipeline ingests millions of events per second into Kafka, then aggregates them in 5-minute windows using Apache Beam. For roads with sparse data, it falls back to historical baselines. This Beam pipeline reads GPS pings, windows them into 5-minute intervals, computes the average speed per road segment, and writes the results to a Kafka topic. The challenge is handling sparse data. If a segment has fewer than 10 pings, it uses historical data instead. Map data changes daily. Google uses a version tile system. Each tile has a version number. When new data is published, tiles are regenerated with a new version. The client requests tiles with a version parameter. If stale, the server returns a 302 redirect to the new version. This allows gradual rollout. This controller checks the requested version against the current version. If they don't match, it returns a 302 redirect with the correct version. This allows clients to update seamlessly. During major events, traffic queries spike 100x. The system uses a content delivery network for static assets and a bounded queue with backpressure for routing. If the queue is full, new requests are rejected with HTTP 503, and the client retries with exponential backoff. This creates a bounded queue of 1,000 entries. When full, the abort policy rejects new tasks, causing the caller to get a rejected execution exception, which can be translated to a 503 response. This is the same issue we highlighted at the start. Here's exactly why that happened. The graph database client had a default connection pool of 100 connections per container. Each connection cached 50 MB of precomputed root data. With a 4 GB heap, 80 connections consumed 4 GB, leaving no room for actual routing. When a burst of requests triggered connection growth, the OOM-killer struck. The fix was simple. Reduce the connection pool to 20 per container, set an idle timeout of 60 seconds, and add a circuit breaker to fail fast when the pool is exhausted. Memory usage dropped to 1.5 GB, and the OOM kills stopped. This is the gotcha from the incident. A connection pool of 100 with 50 MB cache per connection consumes 5 GB. Always profile connection pool memory overhead before tuning heap size. Without a geohash filter, a query for Main Street could return thousands of results. The fix is to limit results and bias by the user's location. Contraction hierarchies are built on static road data. Real-time traffic changes edge weights, which would invalidate shortcuts. The solution is to run CH on the static graph and apply traffic as a post-processing step. If a road segment has fewer than 10 pings in a window, the average speed is unreliable. Outputting it can create phantom traffic jams. The fix is to use a minimum ping threshold and fall back to historical baselines. If each tile has its own version, a user might see a new tile for one area and an old tile for another, causing visual seams. The fix is to version per region, so all tiles in a region share the same version. Never use an unbounded queue like linked blocking queue without capacity. Under load, it grows until the container runs out of memory. Always use a bounded queue with a rejection policy. The contraction hierarchy, CH, precomputation must be versioned alongside map data. When map data updates, the CH must be rebuilt. During rebuild, queries should use the old CH until the new one is ready. Use a blue-green deployment for CH. Keep 2 versions of the contracted graph and switch traffic after validation. The article mentions applying traffic as a post-processing penalty. Here's a concrete implementation. After finding the shortest path on the contracted graph, iterate over edges and add traffic delay from a cache. This keeps CH static while traffic data changes dynamically. The article mentions tile Stampede during map version deployment. A practical mitigation is to use a 2-tier cache, a local in-memory cache, LRU, and a distributed cache, e.g., RAIDs with a longer TTL. During cache invalidation, the local cache absorbs the initial spike while the distributed cache is repopulated. Here are some debugging commands. For routing issues, check graph database connectivity and node existence. For tile issues, verify the tile generation pipeline. For traffic issues, check Kafka consumer lag and restart the stream processor if needed. Let's run through some common interview questions. How does Google Maps handle routing at global scale without OOM? Contraction hierarchies precompute shortcuts, bidirectional Dijkstra on contracted graph. When would you choose a asterisk over CH? A for local city scale routing, CH for global exact routing. What happens when traffic spike causes routing queue overflow? Bounded queue rejects with 503, client retries with backoff. And a few frequently asked questions. How does Google Maps compute routes so fast? Uses contraction hierarchies, a precomputed graph that shortcuts long distances. How does Google Maps handle real-time traffic? Ingests GPS pings via Kafka, aggregates in 5-min windows, falls back to historical data for sparse roads. How does Google Maps update map data without downtime? Uses version tiles, clients request with version parameter, stale versions get 302 redirect. To recap, Google Maps uses contraction hierarchies for sub-millisecond routing, tile pyramids with versioning for zero downtime updates, a stream processing pipeline for real-time traffic, and bounded queues to handle traffic spikes gracefully. Ready to go deeper? Up next, design Airbnb, then design a digital wallet, then design a stock exchange. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.